This lesson is for section 5.4, Properties of Logs. Alright, we are going to do a few different things today. We're going to condense and expand expressions using log properties. So we're going to go more in depth with logs than we did in previous lessons. I'm also going to review finding an x-intercept using log properties. I did that a little bit in your video last night. We're going to use logs to solve equations that would otherwise be something where we would get stuck with an exponential equation. And we're going to use the change of base formula to simplify expressions as well. So here are your three golden rules for both properties of logs and exponents. Notice that they're very similar. This is a review of last year, but when you see a log of a product, so you see a product here, you can actually split this up into the sum of the two logs separately. When you see a log of a quotient, so here's a quotient here, this is the same as the difference between the two logs. When you see the log of a power, you can place that power actually out in front of the log expression. Alright, so very similar to our product of powers, quotient of powers, and power of a power in exponents. So they tie in very nicely. Remember, they're inverses of each other. So let's use these properties to begin evaluating here some expressions. Alright. Now this is a very abstract, I think, idea here because it gives you some log values. It says log with base b of 2 is equal to a, and then log base b of 5 is equal to b, log base b of 7 is equal to c. And then it asks you to evaluate certain expressions here using these three rules. So let's try to rewrite the log here using some of our properties. Well, I see that I have basically a rational power. I can rewrite this as a log base b of 0.4 to the 1/5 power. And now using that last rule we just talked about, the log of a power, I can bring that exponent out in front. So I can rewrite this as 1/5 times log base b of 0.4. Now 0.4 isn't really helpful yet because I'm looking at these values here and I don't have an argument that looks anything like 0.4. However, I can rewrite 0.4 as 2/5. So if I rewrite that as, oops, let me put the 1/5 out in front, of 2/5, now I'm going to use that quotient rule. I don't know where the 1 went. So now I can use the quotient rule, which says that I can split this up and I can take 1/5 times the log of base b of 2 minus log of base b of 5. Now I have 1/5 times this expression here we have a value for. Log base b of 2 is a. So that's now a, and minus log base b of 5, which is this guy here, b. So I have a minus b times 1/5. And that's how I would evaluate this. Now for log base b of 7/16, hopefully this is a little bit easier than the first one that I went through with you. You can just take this, since it's a quotient, right? You're recognizing this is a quotient. You can split this up into log base b of 7 minus log base b of 16. Now here, we can evaluate that right away because that's just equal to c up here. However, this part here we can rewrite. If I want to rewrite 16, I can also think of that as 2 to the 4th power. So if I rewrite that as 2 to the 4th power, I can take that 4, so I have negative log base b of 2 to the 4th. I can take that 4 and place it out in front to make that negative 4 times log base b of 2. So now I have negative 4 times log base b of 2, which I already know to be equal to a. So my final answer here is c minus 4a. And these values are obviously for whatever, base you have and whatever a equals, but that's what you would find. Now I want you to try number 3 on your own and check with the key. Next up, we're going to expand using our properties. So these are way more difficult, I think, than what you would see in 90s. So please make sure you try the you-try problems just to make sure you understand what we're seeing. Alright, now I want to rewrite this as sums and differences. So I don't want to see any products, quotients, or powers in my final answer. Right here I see a product, okay, and I don't want to see that. I also don't want to see a power. So this is, remember, a rational power to, it's the 1/2 right here. So I don't want to see any of that. Now on the inside of this I have a product So the first thing I want to do is split that product up. I know that the log base a of x plus log base a of root x squared plus 1 is equal to this beginning expression. So now I look at this part and I try to rewrite this. This is equivalent to log base a of x squared plus 1 to the 1/2 power. Now I'm going to take that 1/2 and bring it out in front so that I now have, rewriting that first term, log base a of x plus 1/2 times the log base a of x squared plus 1. Now most people try to split this up, okay? This is a big error that you want to avoid. You have to stop right here, okay? This is the final expression for this because I cannot break this up. The log rule that splits it up into the sum only works for a product. It has to start off being a product in order for you to split it up. Okay, a lot of students see this and they think, oh, that's the same as, x squared plus, they'll try to break that up into log base a of x squared plus log base a of 1. Or they do something even funkier and they multiply them or something like that. But it doesn't work like that. So please make sure you just stop when you get to something that looks like this because you cannot apply any of those 3 golden rules. In problem number 5, we have a slightly more difficult looking example, but we're just going to go through it step by step. 1, we see that we have a quotient, right? This is one big fat quotient here. So I know that I can take the numerator, log base a of my numerator, and I'm going to subtract the entire log base a of x cubed times x plus 1 to the 4th. So that's the whole argument here in the denominator. So this was just the numerator minus the denominator here. Okay, and that works because I'm just using that log of quotients. Now, let's work on breaking this up. In the inside of here, okay, I see that I have a product. This is x cubed times x plus 1 to the 4th power. So I can rewrite this, keeping that in the inside of the parentheses, as log base a of x cubed plus log base a of x plus 1 to the 4th. So the one like really important thing here is to make sure that you're distributing this negative after you've rewritten, because I think from here it's pretty simple how to rewrite that, but the main thing that I see with students making mistakes here is not distributing that negative to both terms here. I'm going to show you an alternative way of getting the same exact answer here. I just think that this is a lot more clear for you to write it as a quotient first and then go from there. Okay, now the beginning term here, this first expression here, that's to the 1/2 power, so I'm just going to bring that out to the 1/2. So I have log 1/2 times log base a of x squared plus 1. And I'm going to put that in parentheses just so I know that I'm keeping that together, that argument stays together. Just be really explicit about that because, some of you guys write this out as x squared and then you'll write plus 1, and I can't tell if that's supposed to be the entire argument or not. So please make sure that you put the parentheses around there. Plus it helps too when you're rewriting your own answers in your own test. If you don't confuse that, you're less likely to make mistakes then. All right, now the rest of this, I'm just going to bring this part down because I'm almost done with my final answer here. I'm going to bring this 3 out in front, so I have negative 3 times the log base a of x minus, remember you're distributing here, 4 times, because I'm bringing that 4 out, times the log base a of x plus 1. And again, this is going to stay in parentheses. It cannot be split up. And this would be my final answer here. One quick thing, if you were to start this problem a little bit differently and not think of it as a quotient at first, hopefully you see that you've got this divided by 2 different things. So because it's divided by 2 different things, I could have just started by saying this is log base a of, the numerator minus log base a of one part of the denominator. And then instead of putting a plus sign in between these, even though that's a product on the bottom, you're still dividing this numerator. You're still dividing this numerator here by this term. So you want to make sure you're writing minus x plus 1 to the 4th. Or log, sorry, I forgot the log part of this. Let me rewrite that. I'm running out of room, but minus log base a of x plus 1 to the 4th. Okay, so that's how you could have also redone that same problem without, minus the whole entire product in the denominator. Same thing, but I don't know. I just think it's more clear to do it this way. Okay, Now, the opposite, obviously, of expanding is to condense it. So I want to write this as a single logarithm. So as opposed to the last answers where we saw, a bunch of different logs here, I want to write it as a single log. So what I'm going to do is use the properties in reverse. I see this plus sign here, and when I see the sum of two logs with the same base, they have the same base, and this only works if they have the same base, that means that I can take the product of the two arguments. Now, the one thing you want to do before you multiply by 7 times 3, you want to make sure you're writing this part here and bringing this to the, it's an exponent, and you're going to carry that over. So this is now log base a of 7 times 3 to the 4th power. And you can just leave it like that because I don't really care. As long as you know how to evaluate 3 to the 4th times 7 on a test, you can just leave that right now, right here for your homework. All right, in number 7, I just realized that this is a totally different problem than I actually wanted to practice with you guys. So give me a second to pull up the right problem. Okay, there's the right problem. Okay, now in this problem here, I'm going to leave this 1/3 off till the very end. Okay, so one of the biggest things that I see students make mistakes with is the fact that they don't really pay attention to order of operations. So make sure that you always start from the inside and then work your way out. So you go to the innermost parentheses just like you would with order of operations. So I take a look at this and I notice that this is the sum of two logs with the same base. So I can rewrite that as the product of the two arguments. So this is log base 2 of x times x plus 1. Okay. Now the inside has already been rewritten, and now I'm taking this to, since I have that 1/3 on the outside, I'm going to take this to all of this argument to the 1/3 power. It's not on the outside of the log, it's just the argument. So let me rewrite this a little bit cleaner here. You're now going to pull that and make that entire argument to the 1/3 power. So this becomes log base 2 of the cube root of x times x plus 1. Okay? In number 8, looks a little bit longer, I know, but hopefully you're seeing you've got two sums, so that's just going to be the product of all three of those things. And then this, since you're taking the difference of one of the logs here, it's going to end up being a quotient. Okay, so let's just start with the first 3 terms here, writing that as a product. So we have log base a of, since the overall log here expression, the argument is going to be a quotient, I'm just going to start off right away doing this because I think some of you are going to have a tendency to rewrite this the wrong way, which is to say log base a of x times 9 times x squared plus 1 divided by the log of base a of 5. This is absolutely incorrect. You're taking all of them and rewriting them as a single log. So a lot of students will do this. Just try to avoid making that mistake. It's a common error, but it just goes back to making sure you have a really good base of understanding of the log properties. All right, so anyways, I'm going to take each argument here and multiply them together. So I have x times 9. I'm just going to rewrite that as 9x instead of x9 times x squared plus 1. And then that entire expression here is getting divided by 5. All right, and that would be my final answer here. So that was a pretty short one, pretty easy one. I know it looks hard, but ends up being pretty simple. All right, now I really, really, really beg you, please do these, okay? I really want you to get practice with these and to check with the key to make sure you know how to do each and every one of these, okay? All right, now last thing we're going to talk about is why we need logs. Sometimes we need logs to help us solve exponential equations, okay? There's 2 types of exponential equations that you might see. One where you can rewrite them as the same base. This is stuff we've been excuse me, we've been practicing. This could be rewritten as 2 squared to the x power equaling 2 to the 6th, or 2 to the 5th, sorry. But when you come over here, you cannot rewrite this as the same base. So we need to have a log we use logs in order to solve this. There's 1 of 2 ways to do that, and I'm going to do both ways with you guys. It's up to you which way you like. I know students kind of prefer one over the other. They don't usually use both methods, but sometimes I don't know, sometimes I like using both too. It just depends. Okay, so one of the ways that you can solve each and every one of these exponential equations here is by using the definition of a log. So the first method I'm going to show you is just by using the definition, the algebraic definition of your log. So the first thing I want to do always, if I'm trying to solve for x, is isolate it, right? Which means that I'm going to try to get everything away from that x as much as possible. So I would divide out that 4, and then I look and I see, okay, I cannot write 10 and 1/4 with the same base. You might be thinking 2 or something, but you can't write it with the same base. So now I'm going to use the definition of a log. I know that the log with the base of 10 with the argument of 1/4 should equal x. And that's exactly how I just isolated x. Okay, that's it. You're done. In number 2, again, I cannot rewrite this with the same base. Now, if I want to isolate the x, I'm going to rewrite this. So anytime you get stuck, I think I even have this little note here. Anytime you get stuck in an exponential equation, just rewrite it as a log, and vice versa. If you get stuck in a log equation, rewrite it as an exponential equation. And usually, that's the trick to helping you figure out the solution. So anyways, I'm here and I say, okay, log base 2 of 45 should equal negative 3x. Now I simply divide by this negative 3 to get that x all alone. So I'm left with x equaling log base 2 of 45 divided by negative 3. Now, as I said, we're going to just review this whole idea about solving for an x-intercept. Yesterday when you graphed the exponential function y equals e to the x, it was really easy to solve for the y-intercept because you just plug in x is 0. But for the x-intercept, did I just say the wrong thing? I'm so confused now. Anyway, if I try to plug in for the 0 for the x-intercept, this is a little trickier, but it now should be pretty easy for you. I'm just going to add 5 to the other side and try to get that x alone. So we have now an exponential that cannot be written in terms of the same base, so we change this into a log. We have log base 3 of 5 equals x, and that would be where your graph would cross the x-axis. All right, now, as promised, the other way to solve, which some of you might like even more, is to use the idea that the inverse of an exponential function is just a log. So just like, if I were to try to divide, or I'm trying to solve for x here, I would divide by 3 because it's the inverse operation of 3 times x. So you're undoing the operation. Well, if I want to undo this exponentiation here, I would take the log of base 8 on both sides. So I log both sides. Okay, so log both sides. Now, we know from past experience here that log base 8 of 8, that's just 1. So I'm left with x equaling log base 8 of 23. I don't even have to do really any work here at all. But again, that's the same thing as if you were to just do the definition. If I started with the definition, I could say log base 8 of my argument 23 equals x. So really, you get the exact same solution either way. If I take the log on both sides here, I end up with this, and this is equivalent to x equals log base 4 of 7. I do think that sometimes it's much more helpful to take the log on both sides to actually use the inverse operation. Plus, it gives you a way more, a way solid, better understanding of logs in general. So I would recommend that you do this, even though some of you might be thinking, well, I just like the definition. But make sure you practice this also because it is helpful in a lot of cases. And finally, change of base. So if I have log base a of x that is equal to the log base of anything, so any different base of x over log base anything of a. So what I mean by that is, let's say I have log base 5 of 23. I can rewrite this as the log of any base that I want. So let's say it's 2. I would take that argument and divide that by the log base 2 of my previous base. Okay, that's how I can rewrite that. Now, the reason why this is useful is because in your calculator, you cannot, well, now I think the new ones can actually, but the old calculator models, even those TI-84s, they can't use a different base. So we use change of base here because they only operate in base 10. So we use change of base in order to input that into our calculator. So let's say we want to do that same log here and calculate that. we would put this in as log 23 divided by log 5, because here we're assuming that we have a base 10 and 10. But again, it could work for any base at all as long as you have the same base for each argument. Now, I'm going to show you on your calculator how you would enter that. It's pretty straightforward. You're just going to hit log of 23 divided by log of 5. And that's how you can evaluate this without the ability to write with this base here, because your calculators can't do that. Okay, I think that's the end. Woohoo, we're done. I'll see you tomorrow.